tuning Ramon on hosting this today. He couldn't make it. He had other things to do. And but today I'm gonna be introducing to you the talk by Young-Gyu Park that is talking about the tracking the Pumice rafts from submarine volcano in Japan using satellite and Lagrangian particles tracking. This is a work that it has been submitted to the Marine Pollution Bulletin. It's under review right now. Just to introduce my good friend, Young-Gyu is a professor at the Ocean and Climate Research Center at the Korea Institute of Ocean Research Center, and he's as well adjunct professor at the University of Science and Technology, and also at the Ocean Science and Technology School of Korea Maritime University. He did his undergraduate studies at Seoul National University, and then he obtained his PhD at the MIT Hui joint program in oceanography and ocean engineering. That's when we met. Yep. Back in the 90s. And after doing a couple of postdoctoral stays at Princeton and George Mason University, he joined the Research Institute of Oceanography at Seoul National University. He has taught courses on physical oceanography, numerical modeling, large-scale ocean circulation, and geophysical fluid dynamics. And his interests are large-scale ocean modeling, thermohaline circulation, coastal and regional ocean modeling, geophysical fluid dynamics, climate change, carbon cycle, and marine debris. And I think you are lately specialized in marine debris a lot, no? By the way, the original talk that he was gonna give us, it was about sargassum. Finally, because I'm from the geology department, he decided to put something that was more appealing to to the geology, and I'm the only person here from the geology department. So in any case, if you guys want to have a little bit of, he has another talk on the sargassum, so if there is interest, he can show a couple of slides about that work. It's very similar to this, but with the sargassum. Anyway, Young-Gyu.
Yeah, thank you for invitation, and it's my pleasure to be here to talk about my stuff. He gave us the title. I'm from Korea, and because talk about the science, I will briefly introduce my institute. I guess no one knows about that. Its name is Korea Institute of Ocean Science and Technology, and that's the only oceanographic research institute supported by Korean government. So we are doing everything related to ocean, from coast to polar area. So we go out to sea, make a measurement, and we also do policy, and we go to North Pole and South Pole. We also develop instrument, and we also have we also have an institute who is specialized in shipbuilding and marine plant. We also have some educational section, and we do confer master's and PhD degrees with other universities or by ourselves. And this is one of the pictures we do. We're working at the ocean. And this is one of our research vessels. So we were started about 50 years ago, and the name has been changed many times. Now the name is Korea Institute of Ocean Science and Technology. So now there are about 200 scientists. We have many offices around Korea. This is a headquarters. It's in Busan. This is Korea. We used to be around Seoul, but we moved to Busan about 5 years ago. And we have a Polar Research Institute near Seoul. And this is part of us, but this is much more famous than the headquarters. And there is a institute specialized in shipbuilding and marine plant. There are other small branches around Korea. This island is, I must say, this is a Majorca of Korea. This is tourist attraction in Korea, and there we have a research institute, and they are specialized waters around there. So we have several different branches. These are the facilities we have, the main facilities. This is the largest research vessel. This is a new one. With this, we go to Indian Ocean and Pacific Ocean. There are small ones for the coastal area and the medium-sized ones for marginal seas. And the Polar Institute have their own icebreakers, but that's an independent thing, so I didn't include it here. We have satellite center. This is a geostationary satellite, so it's looking at areas around Korea all the times. During this talk, I will use some of the photos taken by this satellite. So this is about brief introduction of my institute, and from now on, I will be talking about the science part. So this is the content. I will briefly introduce the volcano and Pumice and purpose, and then I will explain the method. Then I will explain the results focusing on trajectories and the way of removing uncertainties in this modeling. Then I'll give you a brief summary at the end. This is a volcano erupted about slightly less than 2 years ago. This is Korea, Japan, and China. This is a boundary of some plates. This is a satellite photo. These are smokes from the volcano. I'm sorry. These are the rocks, floating rocks from the volcano. It floats at the surface, and it's called pumice. It's a it's a floating rock. So what is pumice? It's a volcanic rock with lots of void. So the density is lower than water, so it floats at the surface. So it floats on surface for years until it becomes waterlogged and sinks. Is this rare? No. You might have this in your bathroom. So you could buy it from eBay. The rough surface is good for removing dead skin from your ankle or from your heel. So it's useful, and it's also used in cement. So it could be a useful element on land. But if it gets to the water, it could be dangerous. So when it was erupted, I was missing. Oh no, yeah, it has been changed a little bit. So when it's in the water, it could be dangerous. When it gets to the intake of a boat, it could destroy the engine. When it gets to harbor, it could clog harbors and beaches. And when it gets to beaches, it's threatening local tourism, and it's also dangerous to the fish. So it caused damages to fisheries. When it was erupted about 2 years ago, the areas around this site was worried about their landing because of the damages I showed you earlier. This paper came out last year, and it showed that it traveled a long distance. It started from here, some part went to Japan, Some part went to, this is called South China Sea, and to Thailand and Vietnam, and some, yeah. So it traveled a lot while floating at the surface. So while moving around, it could cause this kind of damages. So to cope with dangers due to pumice, we need to predict the pathways. So around September, August, and December of 2021, some agencies around Korea was making predictions, and Korean government was also interested in if that gets to Korea. These days, there are many satellites observing all parts of the world. So we could trace the movement of the pumice rock, as I showed you earlier. Satellite is almost near real time, but using satellite, we cannot make a prediction. So we need something else. And another problem with satellite is cloud coverage. The satellite, the geostationary satellite I mentioned earlier, takes photos of waters around Korea 8 times per day. But that does not mean 8 clear images per day. If there's a cloud, we get no information. So cloud coverage is another problem. Lagrangian particle tracking could be used for predicting the pathways. For the Lagrangian particle tracking, we need ocean current and wind. Maybe 10 years ago, there are not many data available for ocean current and wind. But these days, there are many good agencies producing good surface, good 3D ocean current data and wind. So it's very easy to get. Even though we are running models for ocean current, for this study, I used something I could get from the internet. The concern with model is its correctness. Is it correct? You could run model anyways, but if it's correct, that matters a lot. This is a basic idea of Lagrangian particle tracking. Let's say your particle is here at time t-1. It will be transported to a new location at time t due to ocean current, this black arrow, and wind. Why wind matters? If the object is completely submerged in the water, it won't feel the wind. But usually floating object has some part above the seawater level, and that's exposed to wind directly. So you could consider this as a sail. This is a boat with a big sail, and this is a boat with a small sail. Boat with a big sail would be affected by wind more than a boat with a small sail. So in this case, it would be affected by wind more, so it would follow wind more compared to this one. Many people did field experiment to find this wind effect. For marine debris, there are some numbers. And for human, there are some numbers. Raft, there are some numbers. For the pumice, it occurs just once in a while. So the windage factor for this pumice is not that well known. Previously, this Jotzeller, they used 1%. This is what they reported. This is about volcanic rocks in near Fiji. That occurred 2019, and we adopted similar method. They compared satellite and Lagrangian particle modeling to make a prediction, and they used 1% or 0.5%, and they argued that 1% is good. But as you can see, there is some substantial difference. So that means the windage factor matters. This is our area of interest. As you can see, This is wind. No, this is ocean current. This is Kuroshio. This is equivalent of Gulf Stream in Pacific Ocean. And this is wind. They are in opposite direction. So if we followed ocean current, it would mainly go to Japan. If the Pumice rock was affected by wind substantially, it could go down south. So if we remember this figure, some portion went to this southern part. So that means wind matters a lot. So main purpose is accurately predicting pathways of Pumice using Lagrangian particle tracking and satellite data. So for that purpose, we need to optimize that windage coefficient. People usually go out to do field experiment, but with these rocks, it's impossible. So we used satellite data and model to get optimal value. So what I'm going to talk about is not complex, no math, just few images and simple numerical experiment. These are the satellites we used. This is Korean satellite. It has about 250 meter resolution, and it takes 10 images per day. But as I said before, the area around Korea is covered with cloud quite frequently, so we get good images once in several days. And we also used Sentinel. That's a bit higher resolution. It takes images 2 to 5 days, depending on the azimuth and their location. So this is an experiment we conducted for this volcano. This is location. We use data from HICOM. HICOM provide daily or sometimes 6-hourly data. So we found that this data is quite nice for ocean current, at least around this area. We suspect that this model is used by US Navy. So that may be the reason why it's tuned very nicely for waters around Korea. US has conflict with China, as you might know. We conducted forward tracking from the volcano. For this particular case, we used ocean parcels developed by Van Seville. We also have our own using MATLAB, but in this case, we use this one. We ran the model for about 6 months from the eruption date. This is the equation. So this is input data. We use ocean current, wind. This is a starting point. So we released about 1,000 particles here, all at the same time, and let it move along with ocean current and wind. This is the wind and ocean current I showed you earlier. This is a Kuroshio. In this area, there are many eddies. So even though current sometimes gets strong, but if we take the mean, it's not that strong. But usually there is a westward tendency. And then this is a Kuroshio. This is quite strong. Sometimes it's more than 1 meter per second. So it's quite strong flow. And there is something called the recirculation gyre of Kuroshio down south. This is a wind during this time of year. So mean of from August to December 2021. So wind is, as I explained earlier, the wind also has westward tendency, but it has strong southward tendency. So it's opposite to the ocean current. For the satellite data, These are the clear images we selected. So we looked through all the images and found that on those days, satellite provided clear images. Luckily, GOES provided good images during the early time. Later time, after November, the rock started to scatter around. So it was a bit harder to detect those using this low resolution satellite. So we switched to higher satellite with higher resolution. So from that time, we used Sentinel-2A and B to track the Pumice rock. So these are the rocks I explained earlier. So what we did was we traced the edges from these images. So this is the initial location. So this is the initial location. That's somewhere near here. So in the beginning, it looked very like looked like a stick line. It's a nice trajectories, but all of a sudden it started to spread into wide area. Around that time, typhoon passed this area. This stream of rock, patch of rock was hit by typhoon, and it spread it into wider area. This also shows the importance of wind factor. So we compared these satellite images with model output. So now I'm going to explain our results. So focusing on pathways and travel time. These are the results with different windage, 0%, 2%, 4%. So the thick, this is a pathways, so thicker line means the major pathways. This is a travel time. So if we look at this one, say in this 0% case, it takes about, it gets to the southern part of Japan, it takes about 1 to 3, about 3 months from here to get to, this is near Tokyo. For the 2.8% cases, it gets to Taiwan. The main pathway is, this is Okinawa. It gets there and then moves southward. For higher windage case, it goes to Japan again, and it moves faster. The reason for the difference is, especially, well, in the beginning we would expect that if we increase the wind, it would show stronger southward tendency. But the tendency was reversed because there's a timing. When it gets to there, when the rock gets there, wind is different, and the ocean current is different, it goes somewhere else. If you compare this with satellite images, you would say this 2.8% is better. So actually we conducted an experiment with several different values of wind factors, and we found this is good. So we could do something, some kind of qualitative estimation, but we want to be more quantitative. This is the main result with my talk. We used something called the skill score. Skill score is used quite frequently in estimating the performance of numerical model. Reviewer said that we should put one somewhere, but in any case, I will explain this one. We adopted this from this paper, Liu and Weisberg. In this study, they compared the Lagrangian particle and a buoy with satellite tracker. So they could track a buoy continuously with GPS. So what they did was to measure the separation between numerical particle and actual buoy. So using the distance between the two, they could estimate the performance of their model. For the raft, we cannot track the raft continuously because our image is available once in a while, and the rocks are similar, so it's impossible to differentiate one rock from another. It's just a big patch. So we modified their method a little bit. So what we did was we ran a model, and then particle got there. So let's say this is a numerical particle number 1. And then we measure the distance to raft, and then found the nearest one. And we assume that that's a match to this. We assume that they are a pair. And then we measure the distance, and then normalize the distance this with the travel length of this particle, as in this paper. Since we have many numerical particles, we did this with another particle, let's say particle number 2, and then we found the nearest one and get the value again. For third one, we did the same thing and get another number. And we did this with 1,000 particles, and then get the mean. So instead of tracking one particle continuously, we used ensemble over large members. So that's the difference. And then we average this again over a certain period of time. So this is our results. So this is S. In our definition, smaller value means better performance. So we conducted many experiments to find the sensitivity to the windage factor, and we found that around 2.8% is better. Another thing we did was changing average period. 15 days, 1 month old. The reason for that is, first one is, once this accident happens, we want to make a prediction as soon as possible. So in this case, we waited until the end. But if it's a real situation, we cannot wait to the end. So first thing was we checked the skill score using images for the first 15 days. For this date, we used 5 clear images. Second one is for 1 month. And this is for everything. Another idea behind this is, in the beginning, the rock is bigger, but as time goes on, it became smaller due to collision. So we also wanted to know would change in shape or breaking matters. But this shows that it doesn't matter. So in this case, we could use 2.8% as a optimal windage value. So there was a typhoon, as I said before. So if we put a wrong number, the raft moves away from the typhoon, so it won't spread into a wide area. But when you put 2.8%, the raft met the typhoon, so it dispersed into a wide area. So later on, so this and this would show quite different destination. So this is a trajectory to March from the beginning. So as this observation shows, some even goes to Thailand, and some goes to Japan. So this is consistent with observation. This is the So this is basically all I have. This is rather simple, as I said before. So we are like 2 years late, but we are now making quite accurate prediction. So if something like this happens, I don't know when it would happen again, but you could use somewhere between 2 to 3% for windage for this problem. And I think the main thing on our is this method. So I think we are providing here way of comparing satellite data and Lagrangian particle modeling. We also do similar thing with sargassum. In that case, we did pattern correlation. In that case, we could have short intervals, but here we didn't. So this is all I have, and thank you for your attention. So if you have any questions. Yeah.
Any questions? Thank you.
In the model, you have put all the emphasis in the currents component and the windage.
Yeah.
But what about the waves? Because
no waves. So we don't have Stokes drift or anything like that. So there is some argument about the Stokes drift and windage. So I must say our windage includes some part of that Stokes drift.
okay.
Yeah. But we don't have that.
Thank you.
Thank you.
It was very nice to listen to that. I've never heard about Pumice before and drifting experiments, so it was very cool. I have a question about diffusivity, because you have satellite data and you could see the spread of the Pumice rocks. Could you compute the diffusivity, or could you include that in the Lagrangian particle tracking model?
We have lateral diffusivity here. Here we used coefficient from Smagorinsky, and R is a random number between 1 and 0. So this is a bit unclear part. That's always unclear because we are using output from different model. So if we run this in a numerical actual model, results might be slightly different, but I think the general tendency is similar. One of the reasons I'm saying that is it's a different case, but sometimes we did a backward experiment without diffusion. And backward and forward, you are usually similar within, let's say, like few months. If we run for years, it might be different, but for few months. Yeah.
I have a question. How long it takes to run these simulations?
Not that long, few days maybe. Yeah.
So if you want to make it in operational mode, is difficult.
Yeah, it's possible. It takes about few days to run for 6 months.
Oh, okay.
So 6 months. So in this case, we use this ocean parcels. That's also available, and it's written in Python. So you could run it your PC or in your Mac. The difficulty is this getting proper ocean current and wind. In this case, we have some experience with this product, so we started right away. But For other areas, you might have to verify those current data.
And another question, some of the pumice probably doesn't float, it just stays just below the surface.
Yes.
Do you also account for those, or?
We have no idea about that. And this paper, was that? In that paper, they also looked at distribution at the bottom. They did geological survey, so they found the change in location, but we don't have that data.
No one else? Well, thank you again.
Thank you. Yeah, thank you for your interest. Thank you.